Okay, last lecture, we were at this particular point, I think. We had looked at a differential pair with an active load, and the load is connected in the form of a current mirror here. And we had seen that this particular stage has, current mirror load has several advantages as compared to a differential pair stage where you simply connect PNP transistors as an active load which have a bias of their own. And the comparison tells us several advantages. The first one, of course, is you don't need a separate bias circuitry to generate V bias here. This is biased by itself, by the differential pair itself. And the second part is the bias here is very sensitive to, or the Q point or quiescent point is very sensitive to this voltage here or the supply voltage here. And we saw that is very difficult to maintain both of the transistors in active mode here. And here, of course, Q3 is in active mode and Q1 also is then in active mode here. And so bias point is pretty stable here. The other one is differential gain we saw was GM1 R02 parallel R04. If we do the calculation, differential mode gain is half as compared to this particular stage here. And common mode gain we can calculate from here. It's R03 by 2 R05 here. While common mode gain, we couldn't derive an expression because it requires a much more exact analysis without making approximations. And common mode gain, all that we are saying is it's much smaller as compared to this particular stage here. So if you just look at these two amplifiers here, the only difference between these two is just one single wire that you've taken from here and connected it over here. All right. One single wire causes a doubling of gain. Doubling of gain causes common mode gain to become much smaller here. And this is one of the characteristics of analog circuits. A small change, apparently a very small change, can have a very large effect on the characteristics here. All right. So let's go on and let's discuss further. So this would be the last discussion on differential pairs. And we take up MOS differential amplifiers now. So far, all our discussion has been with BJT differential pairs. And MOS differential pairs are very similar. So I'm going to just breeze through the analysis here. So the simplest differential pair then is your two NMOSs here, biased by a resistor here, RSS and BSS here. And the load here is a resistance RD here. All right, so that's the simplest differential pair that you can think of. Of course, you can make it with a PMOS as well. And then the whole thing becomes, RSS will come at the top here, and these will come to the bottom here. Anyway. All right, so as usual, bias point analysis, what you do is you remove the signals here, you put it to ground. And so again, I'm not calling it DC analysis, I'm calling it bias point analysis here. Okay, and as usual, what happens is, what you need to do is calculate this current. And this current that you see here, ISS, that will divide equally between these two transistors, which have been assumed to be identical. So the bias currents would be half of ISS here. ISS here that you see will be equal to the voltage at this point. Voltage at this point here will be nothing but, if you assume it to be 0 here, then the voltage at this point is minus VGS of this particular transistor, minus VGSQ. And the voltage at this end is VSS here. So the net current that flows here is minus VGSQ minus VSS by RSS. So what is VGS? VGS is, from assuming the transistors in saturation region, VGS is VTN plus square root 2 IDSQ by beta. There's only, so we have now these three equations together. And there's one more equation. We have to keep in mind that the body of NMOSs is always connected to the most negative point here. So the body is connected to minus 3.3, while the source is at some other potential. So we have to take into account the fact that threshold voltage is different than the zero bias value here. So we have to use this expression for calculating the threshold voltage here, which depends on source to body voltage. And source, we know, source at this end is nothing but minus VGSQ. The body is at VSS here. So source to body voltage we know is over here. So we have all these equations that you see here. We have to solve them together. to arrive at what is the drain current here and what is the drain current here. Now, because these equations are coupled together, so although they are simple, it takes a little bit of time to solve them in a consistent manner. And as usual, what we do is, a simple way of doing it would be, what you do is, start with a VTN, which is basically VTN zero bias value here. And then, so you use VTN here. Then, if you look at these two equations here, they are nothing but, so you can take VGSQ here and substitute this expression here, and ISS is nothing but half of IDSQ. So you get a quadratic equation, which you can solve to get the value of IDSQ and VGSQ. Once you get that value, then you recompute a value of VTN and do a couple of iterations, and the answer, all you require is maybe 2 to 3 iterations. And because the equations are not highly nonlinear, and therefore 2-3 iterations is enough to converge and arrive at the answer. All right, so conceptually simple, but a little bit of effort is required to find the bias currents. As an example, when we have 100K here and we have 27.7K here, these are the values that one gets. 25 microamperes is the bias current here. And note, the zero bias threshold voltage is 1. The actual threshold voltage of M1 and M2 is 1.42. And the reason for this is the body effect here. The source is, you can see here, the source voltage will be minus 1.92 here, minus 1.92, and the body voltage is minus 3.3, and that causes the change in the threshold voltage here. All right, so threshold voltage, then you cannot assume it to be 1 volt here in these NMOS transistors here. You can see it's substantially different from 1. It's 1.42. All right. The next thing is, so after doing the bias point analysis, we know the current in the transistors here, and we know the bias voltage here, V01 and V02. The next thing is we go and look at the small signal here. But before I do the small signal, very quickly, let me show you what happens if you apply a signal which is large enough. Signal which is large enough so that you can't solve it using small signal here. And one of the properties, of differential pair is that when you apply a voltage here, whether it's small or large, but you can see its effect more in large here. When you apply a voltage on one end, let's say, so what happens is, let's say this voltage is positive, and as we increase this value here, what will happen is you are increasing the gate here. So as you increase the value here, it results in an increase in value of this particular voltage here. Note that this voltage will travel like this here, VGS here, so it increases this value here. So what it does is it reduces the value of VGS of this transistor. So when you apply a positive voltage here, effectively VGS of this transistor increases, while VGS of this transistor decreases here. So in effect, what happens is drain to source current here increases and drain to source current here decreases. And note that these voltages that we apply from this side are not very large. So so as to alter the value of ISS here. To the first order approximation, ISS, roughly the current that flows here, it remains the same. And therefore what happens is more of ISS starts flowing through M1 and less through M2 here. And if you apply a voltage large enough, then what will happen is this entire current ISS that you see here shifts to M1 and nothing flows through M2. And the same thing will happen if you apply a negative voltage here. If you apply negative, this ISS shifts to M2, increasingly shifts to M2. And if the voltage is large enough and negative, then this entire current will flow through M2. And whatever is happening with voltage here, you could take this voltage and put it over here, and the effects would be the same here, except that when input voltage is positive here, the current will shift to M2. So these two graphs, they basically show that particular property here. You can see what is happening is the currents are, so the voltage along this is, along this axis I have voltage here. So at 0, the two currents, you can see here IDM1, this is the current here, the red one is the current in M1, and the other one is the current in M2. So the two currents are exactly the same as we expect when the input voltage is 0. Now when I make the input voltage positive, the current, you can see here, current in M2 decreases and the current in M1 increases. The sum of them will be approximately constant, almost constant here. Note that I require only about 200 millivolts or so here to cause a complete switching, of current from, to M1. The entire current is flowing through M1 and current through M2 is 0 here. Same thing happens when you go towards the negative here. When you apply minus 200 millivolt here, the entire current shifts to M2 and nothing flows through M1 here. Alright, so this is a current switching property of a differential pair. Now obviously if the current is switching, then V01 and V02 also change. So these are the plots of how V01, so if the current is increasing here in M1, the V01 is decreasing here because more drop takes place in RD here. So V01 decreases here. And if current in this branch reduces, then V02 here increases here. So it's the same property that you see in current, except that if the current rises, the voltage falls at the output here. Alright, so that's the current switching property here. And as I said, this is more interesting when you use a differential pair more for switching applications. When you apply large voltage here, then only one is interested in this kind of characteristics. Normally what would happen is we use a differential pair as an amplifier and the voltages that we apply are small in magnitude. And therefore, small signal analysis is sufficient for us to find out the values of currents and voltages in the circuit here. And in a differential pair, if you have, in general, you can apply two different voltages, VI1 and VI2. And what we do is we define differential voltage, which is this difference of the two, VI1 minus VI2. We define a common mode voltage, which is the average of the two. And in terms of VID and VIC, we can write VI1 and we can write VI2 here. So we do all the analysis in terms of differential mode and common mode here. So the input voltage VI1 that you see here can be written as a sum of a differential part and a common mode part. Similarly, VI2 can be written as a sum of differential part and a common mode part. We have seen this with a bipolar, so I'm going over it pretty fast here. So a differential pair then with an arbitrary voltage applied here and an arbitrary voltage applied here can be represented in this form. With a signal which is differential here, VID by 2 and minus VID by 2, and a signal which is common mode here, VIC and VIC. Okay, so we write it in this form. And then what we do is we do two kinds of analysis. Because we are doing small signal, circuit is linear, we use superposition. So first we take VID by 2 and minus VID by 2 here, and we get this part of the circuit here, which is a differential mode analysis. Then next we take VIC and VIC here, and we get a common mode part here. So we analyze this one, and we find out all the voltages and currents. We analyze this one, we find out all the voltages and current. The net voltage here will be the sum of voltage that you arrive at here, plus the sum of the voltage that you arrive at here. So superposition is what we are using. So analysis then is differential mode and common mode. When you come to differential mode, note that the voltages are VID by 2 and minus VID by 2 here. And then what we do is we use symmetry. M1 and M2 are identical. And therefore differential mode analysis it tells us that this node is small signal ground here. This is small signal ground, positive here and negative here. There is no other possibility except for ground here. So this becomes ground. And the two halves of the circuit, they separate out. RSS doesn't matter anymore. And so if you look at the left half, it's nothing but a common source amplifier. And you look at the right half, it's also a common source amplifier. So we simply write down the expressions here. V01 divided by VID by 2 is minus GMRD. And therefore the ratio of V01 and VID is minus 0.5 GMRD. And this is what we call as the differential mode gain. So this is the value at this point here. Similarly, we can write down expression here, V02, which is also same 0.5 GMRD, except that the sign here is positive. So the voltage that you get here is negative. You can see here minus 0.5 GMRD. The voltage that you get here is positive here, 0.5 GMRD. So the two voltages, the magnitudes are the same, but they are 180 degree out of phase here. So that's differential mode. Common mode, you apply the same voltage on both sides here. And in this case, what we do is, in order to use symmetry, what we do is we split RSS here into two parts, two RSS on one side, two RSS on the other side here. Now we can clearly see a left half and a right half. In here, both of them were coupled together. So we separate them into two halves. We note that from symmetry, the current flowing through this wire will be 0. And therefore, we can cut the wire here. 0 current means open circuit here. We can cut it. And so we get two halves of the circuit. Both halves are the same. And this now the gain we can easily write. The gain of this particular part will be effective GM. We all know when you have a resistor connected into the source is GM by 1 plus 2 GM. GM by 1 plus GM multiplied by the resistor which is there in the source. So 2 RSS here. Multiplied by the resistor in the drain, which is RD. So we get a common mode gain, which is V01 by VIC. So both sides are the same. So that's the strategy that we use for calculating common mode. So we have differential mode gain, we have common mode gain, we can take the ratios and we get CMRR, and CMRR then depends on the value of resistor here. Okay, that's the resistor which controls CMRR here. Now, we can plug in the value of GM here. GM will be IDS, 2 IDSQ by VGSQ minus VT here. And this tells us 2 IDSQ is nothing but ISS here. So this tells us that we drop ISS into RSS, control CMRR here. And ISS into RSS, we can write it as minus VGSQ minus VSS here. And anyway, so all that, it basically depends then on how you bias the differential pair here. And the message here is CMRR is pretty low, and to a large extent it is determined by the supply voltage that you have. And for supply voltages of 3.3, you don't get enough CMRR. And so the strategy for increasing CMRR, if we go back to our expression here, CMRR depends on RSS here. So what we do is we take RSS out and we replace it by a current source here. A current source ideally will have a infinite RSS here. So that's what we do in order to improve our differential pair. So we focus on RSS here. Ideally, if you take RSS out and replace it by a current source, if you do that, then the current source resistance is infinite. A small signal, note that CMRR is also a small signal quantity. It's the ratio of small signal differential gain and small signal common mode gain here. So when I look at RSS here, I'm talking about a small signal value of this element here. So when you look at a small signal resistance of this element, it is infinite, and therefore you'll get CMRR, which is also infinite. But we know that we cannot build a ideal current source. It doesn't exist. So what we have to do is realize it using a transistor. One way of doing it is simply taking it NMOS here, applying some bias voltage here. Okay, so that acts as a current source, a transistor biased in saturation region. NMOS acts as a current source. We know that the resistance of this one, when I look at it from the drain side, is simply R0, R03. So CMRR of this one will be GM1 times R03. And this GM-R0 product is now substantially larger than the value that we obtained. So you can easily get a CMRR of 100 or 200. Okay, but still it's not too large because the GM of a NMOS is not as large as GM of a bipolar. So you don't get very high CMRR. All that you'll get is maybe 100 or 200. If you want a better value of CMRR, then what you need to do is build a better current source. And one way of doing that is you stack 2 transistors here. You add one more transistor here. And now if you look at it from the drain side, what happens is if you look at it from the drain side, I'll leave it for you to show that the resistance that you see from the drain side is not just R03 of this transistor, but that resistance gets multiplied by GM3R04. Okay, so the effective resistance that you see from here now becomes much larger here. Much larger here, and CMRR now you can get, which is 1000 or 10,000, very high values of CMRR you can get here by building a better current source here. All right, so that's how you improve CMRR, when you're improving CMRR, what it is doing is actually reducing the value of common mode gain. Differential mode gain is still GMRD. You're not touching the differential mode gain at all. By going from here to here, you're reducing common mode gain and you're increasing CMRR. So if your differential mode gain, if you want to increase, the way to do it is replace RD by a load here, by a active load here, which is a PMOS here. Now we saw for this transistor, when you use it in this manner here, just like bipolar, we saw biasing is very sensitive to the voltage that you apply here. Biasing is very sensitive to VDD here. And therefore, this is not a good stage to use. And what we do is we replace it M3 and M4. We don't use it in this manner here. We still put M3 and M4, but we use it in a current mirror form here. We connect drain and gate together here. So this is what we call as differential pair with a current mirror load. All right. So this is the stage then, which will give us a very stable bias point. We'll have differential mode gain, which is higher than this. will have common mode gain, which is actually lower than this. So we'll have all the advantages, and therefore this stage is seldom used, and this is the one which is one of the most popular differential pairs in MOS technology here. So differential pair here with a current mirror load here, and here you have a current source biasing here. So let's look at it in a little bit more detail. A bias point, as usual, what we can do is the moment you have V bias here and you know VSS here, so you know the effective VGS of this transistor, so you can determine what is ISS here. This transistor is in saturation region, so the ISS you can calculate from this expression here. Once you know ISS, we know that the two currents are going to divide equally, so you know the IDS-Q1 and IDS-Q2. Alright, now it's not so obvious why they will divide equally here, because the two halves of the circuit are different. You can see here the circuit is no longer symmetrical. The voltage here, the gate and the drain are shorted together, while here gate and drain are not shorted together here. And note that M1 and M2 are identical. Their gate to source voltages are also identical, but their drain to source voltage here can be different. If we look at this particular circuit, can be different, and therefore we know that the current does depend on the drain to source voltage here. There is 1 plus lambda times VDS here. But I'll show you in a minute that if M1 and M2 are identical, M3 and M4 are also identical, then one can show that V01 will be exactly equal to V02 in a MOS differential pair. The value here will be exactly same as the value here. Okay, I'll show you in a minute. But assuming for the moment that V01 is same as V02, then one can say that the currents in M1 and M2 are identical, because same drain voltages, same gate voltage, same source voltage, so currents have to be the same. So once you know the current here, then I can easily determine what is the voltage at this node here, because the voltage at this node is nothing but VDD minus the source to gate voltage here. And once you know the current in M3, the source to gate voltage you can similarly obtain from the expression for current here. So this point then is very well defined, and as I said, this point is exactly same as this one here. So let me prove it to you that the two voltages are going to be the same in a MOS differential pair here. Alright, I'm going to do it in a more general case. This is a ground here and a ground here, and a more general case is where I apply the same voltage here and the same voltage here, which means the voltage is a common mode voltage here. As a special case, it can be ground. I can apply 1 volt here and a 1 volt here. Still, I will show you that the two voltages will be exactly the same. So the way we do it is the way you've been doing some of the proofs in your school days, by contradiction. Okay, so we'll assume that the two are not equal. So if the two are not equal, one way of saying it is, let me assume that V01 is larger than V02. Okay, so if V01 is larger than V02, focus on M3 and M4. If I look at M3 and M4, what I see is the transistors are identical, their source voltages are the same, their gate voltage is also the same, right? And therefore, I can say the following here. The other thing I will note here is if V01 is larger than V02, the source to drain voltage of M3 will be smaller than source to drain voltage of M4. Okay. Now the current that flows in M3 is current in saturation region. In addition to that, I've taken this value here also to be more accurate, channel and modulation here, 1 plus lambda VSD3 here, VSD3 here. And similarly, the expression for current in this transistor with VSD4 here. Now we note that if we look at M3 and M4, everything is identical except for their source to drain voltage. And since we have said the source to drain voltage of 3 is less than source to drain voltage of 4, we have to say that ISD3 is less than ISD4. Now how much it is less and all that will depend on what the values are. But in general, we can say this condition implies that source to drain current of 3 is less than source to drain current of 4. Alright, that's what this condition is telling us. Okay. Now, so let's focus on M1 and M2 then. If I take an M1 and M2, V01 greater than V02 means VDS1 is greater than VDS2. Because the source voltage is the same, drain voltage is V01 here, drain voltage is V02 here, so we can say this condition here. VDS1 is greater than VDS2. So now if I look at M1 and M2, the current in M1 is 1 plus lambda VDS3, VDS, it should be VDS1 here. The current in M1 will be VDS1 here, and the current in M2 will be VDS2 here. Because VDS1 is greater than VDS2, what we are saying is IDS1 is greater than IDS2. Now, we know that actually IDS1 is same as this current here, and the current that flows is same as current here. So we've ended up in contradiction here. Our results are not consistent. This, if I assume VSD3 is greater than VSD4, is telling us the current here should be less than current here. But then this one is telling us that the current here should be greater than the current here. And the same current flows through both. So which means that we cannot assume V01 greater than V02. The results that we are getting are contradictory, and therefore this condition cannot hold. V01 greater than V02 cannot hold here because we don't get consistent results. Now, same thing I can repeat by assuming V01 less than V02 here. You can start by assuming V02 greater than V01, and again you will end up showing that you can't get consistent results. So if V01 cannot be greater than V02, if V02 cannot be greater than V01, the only possibility that you are left with is that both are equal. V01 is exactly same as V02. Alright, so in this case now what we are showing you is that if you apply the same voltage here and same voltage here, transistor M1 and M2 are identical, M3 and M4 are identical, there's no other possibility except this voltage being exactly same as this voltage. Okay, and you go ahead and you do simulation and you find that under all conditions you find that the two voltages are exactly the same. So it matches with what our expectations are from this particular analysis. So then let's go back, and then that's what I said, that when I put ground here and ground here, V01 is exactly same as V02 here, and therefore the currents are the same, and whatever voltage you calculate here through this expression, the same value of the DC voltage will be at this particular point here, bias point. And therefore the bias point is extremely stable because the current is decided by here. Once you decide the current, then the source to gate voltage drop here gets decided, and therefore V01 also gets decided. Alright, so that's the bias point here, and common mode part. So now we have to do small signal analysis here. So common mode part, we just saw that when you apply the same voltage here and the same voltage here, this voltage is going to be the same as this voltage here. We just showed that in the general condition, when the voltages are the same on both sides, the output voltages will also be same on both sides. And so whether the signal is small or large, we didn't assume anything of that kind here. The signal could be small, the signal could be large, the voltages will be the same. V01 is same as V02. So we can use that result for our common mode here. And so as usual, what we do is the transistor M5, when I look at it, small signal model, it's R05 here. We have split R05 into two resistors, 2R05 and 2R05 here. Now, even though when you look at the circuit, it appears to be asymmetrical because of this, but note, V01 is exactly same as V0. The two voltages are exactly same. So if we focus on the circuit below this particular line here, what we find is the drain voltages are the same, source voltages are the same, gate voltages are the same, and therefore the current here and the current here are going to be exactly same, and no current should flow into this particular wire here, and therefore one can cut this particular wire here. One can cut it, and one can get a circuit on the left half which is like this. On the right half, you get a circuit which is different. On the right half, you get a circuit which is R05, you get M4, but to the M4, whatever value you determine here, the same value will appear over here. Okay? Same value will appear over here. But note, even though the right half, let's see if I have the right half here. Okay, so the voltage that V01 is going here to the gate here. But what did we tell also? That V01 will be exactly same as V0. So what you get is, you get a voltage here which is same as this voltage here. In effect, what do you see? It's as if the gate and the drain are shorted together because the voltages are exactly the same. So you might as well, if you want, you can take a wire here and connect it here. It's not going to make any difference because the voltages are the same. So on the right half also, you have exactly the same circuit here. Okay? Now, when you have the same circuit, note that when you have a transistor whose Gate and drain are shorted together. The transistor acts as a resistor whose value is 1 by GM3. Whose value is 1 over GM3. And when you have a transistor with a resistor connected in its source, its effective GM is GM divided by 1 plus GM, whatever is the effective resistance here, which is 2R05. So your common mode gain then is given by this value here, and it's very precisely defined here. And GM1 times R05 is much larger. All right, so what am I trying to show here? Okay. So common mode gain, unlike a bipolar transistor, where this result was not true. In a bipolar, V01 was not equal to V0 here. The reason being, differences was that in a bipolar, there is a base current. There's a base current that flows from here, which makes the currents in this side different from this side here. And therefore, we could not use this simplification here, V01 equal to V0 here. Okay, so in a MOS, the analysis is simplified, and we get a common mode gain, which is pretty small here. Now, just like in a bipolar transistor, suppose I didn't have this wire here as a current mirror load. If I had built a differential pair with simply a PMOS load biased in this particular manner here, we would have calculated a common mode gain, which is given by this expression here. See, here, drain and gate are shorted together, so the resistance of this one becomes 1 over GM. Here, the gate and drain are not shorted together. The resistance of this branch is R03 here. So you would have gotten a common mode gain, which is R03. And if you compare the two expressions, you can see here, common mode gain is much smaller than this value here, because 1 over GM3 is much smaller than R03. So that's the advantage that you get by building a current mirror load here. Common mode gain becomes much smaller here. Okay. Differential mode analysis is more complicated. We had done that for a bipolar. The way we proceed is as follows. We build a Norton's equivalent at this particular point. When the circuit, if the circuit is very simple, like a common source or a common gate, you can very quickly analyze. If the circuits become more complicated, the strategy that we are adopting is at whichever node you have to calculate the gain, what you do is at that particular node build a Norton's equivalent. And that involves two things. One is calculate Norton's current. So you take that particular node, short it, and calculate the current that goes into that particular node. And in this case, the analysis is exactly the same as bipolar here. So the idea here is, let me repeat, the idea here is that V01, because M3 is connected in a diode manner, so the resistance between this node and the ground is small, and this voltage then is pretty close to 0. It's not 0, but this voltage is very small. And because this is very small, and this obviously is ground, and then when we look below this particular line here, we see M1 and M2, we see positive voltage applied here, negative voltage applied here. What we can again assume is that this node is like a virtual small signal ground. So just like in a differential pair earlier with a resistive load, we do the same thing here. This becomes ground here, and this becomes ground here. All right, so that's an assumption, keeping in mind that V01 is approximately equal to 0. Next, what we do is, the current that you see here, IN, it has two components, I2 and I4. So we find out I2 and we find out I4, each one of those components. And the way we do it is I2 now, note, if I look at this particular circuit, this one is ground here, and there's a voltage attached to the gate here. And note that when you look at a transistor from the drain side, what do you see? You see a current source in parallel with R0. What is the value of current source? GM VGS. And GM VGS is nothing but 0.5 VID, so that's the current source here. Plus there should be a current which flows through the R0. But note, one end of R0 is ground, the other end is also ground, so no current flows through R0. Okay, so that's why the current I2 is simply GM times VID by 2. This is the current here. So I2 is straightforward. I1 is also, if I look at it from the drain side here, the current I1 is also GM1 times VID here. Of course, there is a R0 connected here, but R0, the R0 that you see here is a very large resistor, and the voltages are very small here. V01 is a very small voltage, very close to ground here. So again, the current that flows through R0 is negligible, and I1 is also GM1 times VID by 2 here. So now one can do a more elaborate analysis here, but note that this current I1 will flow through M3. And if I look at M3 and M4, they are like a current mirror. So which means whatever current flows through M3, the same current flows in M4. So well, you can do a more elaborate analysis and go ahead and show, but straightforward also is whatever current I1 is there, I4 will be the same value. Okay, and all this analysis will show you the same thing here. So what ends up then is that we know I4 is nothing but GM1 times VID by 2. We know I2, which is minus GM2 by VID by 2 here. And you sum them up together and you get IN, which is GM1 times VID here. That's the Norton's current here. Note the advantage that comes by connecting this part here. The advantage that comes by connecting this wire here in a current mirror is whatever is the current flowing in this part gets mirrored here and then contributes to the Norton's current. If I had not connected in this manner, if this had been ground, then whatever is the current here doesn't get coupled here. Okay, doesn't get coupled to the other half here. That's why we get GM1 times VID here. If you make it ground, you can do the analysis by making this node ground here. Remove the wire and make it ground here. All that you will get is then you'll get is half GM1 times VID. So Norton's current gets doubled by building a current mirror here. So that's why you get a gain which is double here. The output resistance or the Norton's resistance is resistance looking from here. So you remove all the sources and the net resistance is Vx by Ix. So what we have to do is calculate the components of Ix, I2 and I4 here. And again, as Ix will be here. So we start building current for I2. And when we look at I2 here, so we have a transistor with a gate to ground. When we come to the source end here, we have RO5, of course, and then we have resistance looking into the M1 here. So when you look into the source of M1, what you see is a resistor which is 1 by GM1. So you see a resistor which is 1 by GM1, and that's much smaller than the resistor R05, so you can forget about R05. And the net resistance then looking from the drain side is simply equal to 2R02. When you look at it from the drain side, the resistor is R02, 1 plus GM2 multiplied by the net resistance in the source, which is 1 over GM1. And so the current I2 then is Vx by 2R02. Now, interestingly, what happens now is this current I2 that we just calculated, it starts from here, goes here, comes here, and then eventually to the ground. And what it does is, at this point here, it sets up a voltage. It sets up a voltage at this particular point, which is equal to I2, this current here, multiplied by the net resistance of this branch, which is 1 over GM3. So what you do now to calculate I4, you focus on I4 now, M4 with the voltage V01, which is given here with the other end ground. And so you have now a simple transistor with a voltage applied to the gate and with the source at ground. So you can easily calculate what is I4. I4 has two parts. One is GM, VGS, and the other one is Vx by R04. So now you take V01 from here, plug it here, and after that is simplification, and one can show that I4, finally one can show that Ix is given by, it appears as if the R0, the resistance here and the resistance here are in parallel here. So Norton's resistance then comes out to be R02 parallel R04 here. So after that is only algebra. I've given you I2 and I4. It's just simplifying, putting it together, and shows that the resistance looking from here is R02 parallel R04. So now, so we've done an elaborate analysis to show that effective resistance is given by here. Now, as I said, many times in textbooks you will find that what they do is they simply say that this node is ground, and they will say that this voltage is also ground. And if this node is ground, then resistance looking down, is simply the resistance of M2, which is R02. And similarly, if this node is ground, then if you look up, all you see is R04, and therefore you get a resistance which is R02 parallel R04. You get the right result through a wrong procedure. This node is not ground. We just saw what happens is there is a resistor 1 over GM and the current starts here, flows here. It's much more complicated. Okay, so we have now our Norton's current here, R02 parallel R04. We have Norton's resistance here, which is GM1 times VID here, and net voltage then, the whole circuit then appears as a Norton's current in parallel with the Norton's resistance here. So the net voltage at this particular node, V0, will be Norton's current multiplied by Norton's resistance here. So GM1 minus of Norton's current here multiplied by Rn here, and therefore differential mode gain is GM R02 parallel R04. So the final expression is very simple. GM of this transistor, M1 and M2, they are the same, multiplied by the net resistance at this point, which is resistance looking up of R04, and resistance looking down, which is R02. Okay. So the final result is the same, and this is a comparison between the two. As I was saying, ADM is GM, R02 parallel R04, ACM is given over here. If you don't connect it in a current mirror manner, the differential mode gain is half, the common mode gain is much larger as compared to this one. So this circuit has all the advantages compared to this one. Bias point is pretty stable. Differential mode gain is double. Common mode gain is also much smaller here. Of course, now this circuit has a certain amount of differential gain. If you want to build higher gain, now the strategy for building higher gain, if you recall, is you don't just take one transistor, you stack transistors. So what you can do is you can make better current mirrors here. And you can, you can stack transistor here and transistor here, and you can build better current mirrors to increase the gain here. Not only that, M1 and M2 can be connected in the form of a cascode also. Cascode here, which means that you connect another transistor, let's say M5 or something, which is a common gate stage, and this is like a common source stage here. So one can build more complicated differential pairs, but let's stop here as far as a differential pair is concerned. So we are done with our differential pairs, and I think we have 2 or 3 lectures left here. Probably 3-4 lectures left. So what I'm going to do is from next lecture onwards, I'm going to start with op-amp and build a very simple BJT op-amp. I don't think we'll have time for a MOS op-amp here.